So are there any questions from what we did in the morning? Good.
Sir, I have a question. Sir, the question is in commutation relation for the field, you wrote something pi and pi will be I delta cube, the delta function. So delta function's value will be infinity. It's at point x equal to x prime. So in the normal commutation relation, we have delta ij, which is finite value. So, sir, what will be the uncertainty principle for the continuous
So
value?
you have to look at smeared operators. Sorry, this is something. So you're right, this has some value which looks like this. The operators which have finite uncertainty are, and the ones which are observable actually, are the ones where you smear this. And then you smear this also. Okay, when you do that, you will get an integral here also. Which actually looks like, here I'm assuming f is real, okay? And now this guy has finite uncertainty. Okay, do you see?
Okay, sir.
Smear the operators to get something which has finite uncertainty. That's something. What? Which have different smearing functions. No, you can integrate this commutation relation with phi and some other pi also if you like. That's fine. But the important point is that to get things which, so you'll get something else. You'll find phi and pi with some g is something. This is something which is generally true in quantum field theory, which is that often to get finite answers. Well, you either need to separate points, and when you have delta functions, the way to deal with them is to smear. The operators in quantum field theory are not really functions. These are what are called operator value distributions, which means that they make sense when you integrate them against well-behaved functions.
Okay, sir. Thank you.
Okay, good. Is there any other question? Okay, good. Okay, good. The AC on here? Don't have any ventilation. It's on. It's on, right? Can I get the remote? Can I get the remote? Yeah, I just want to at least lower the temperature. It's 28. What's the use of that, man? 20. Well, I actually like something like 19, but I'll keep it at human temperature for you guys. Now this one is where? How do you know what this one is at? How do you know which one is getting controlled? But how do you know what the current temperature is? Because now this has become 20. Okay, fine. Let's try. Let's hope it works. Otherwise, okay, good. Okay, good. So this is something generally true. Okay, in quantum field theory, you have to smear things to get well-defined answers. Okay, good. So now, I want to describe a little bit about this issue of localized excitation. So we discussed causality, and what we've shown is, oh, by the way, I forgot the factor of I. There is a plus I or minus I, which I promised to check, which I forgot to check in one of the integrals, whether it should be plus ij or minus ij. Okay, I'll check by next time. Otherwise, you guys can also check. It's just some integral. What we showed in the morning was that this was equal to 0 when okay. Yeah, so when these things are space-like separated, this is equal to 0. Now I want to explain a little bit the notion of a localized excitation. You see, remember that we discussed at the beginning of this class why this thing called X. Right? If you just did single particle quantum mechanics and tried to write down a position eigenstate, it would not be a localized excitation. Remember we discussed in the beginning of the class when we did this, how this had support even, when x minus x prime was larger than t. Okay, good. So you could ask, is there a notion of a localized excitation? Do you have a notion of something that can be localized in quantum field theory? Do you guys have any ideas? How would you create one? Given what we have learned about locality and so on. Okay, good, very good. Let's say we did that. Is that a localized excitation? Okay, that's a good try, but does it really work? So what you're saying is, let's take the vacuum and let me smear it. Yeah, so if you smear it, you'll get a normalizable state. And this is over some region R. So this is the region R. Is this really a localized excitation in the region R? Okay, okay. Why don't you think about it? So let's say okay. So let's see if since this is anyway an extra class, let's try and be a little slower. Yeah. So think about it. Is the state a localized? What do you want to check, right? Whether this is a localized excitation or not. You see, what you want to check is that this. You see, there's a universe outside, and there's some region R, right? So if this was a localized excitation in R, what would you want to check? Well, all observables outside should be the same as they are in the vacuum, right? So what you want is that psi O psi is equal to the vacuum for all O which are space-like to R. Is this clear? O is an operator, it's localized in some place. We are not being precise about where it is, but it's localized in some region which is space-like to R. I'm not putting in brackets. If this was localized, then you would want that the observables of O, whatever you observe, right, observations of O, give you the same answer as they give you in the vacuum. So an observer who's measuring O thinks that the state size is exactly like the vacuum. That's what you mean by localized excitation, right? Something is here, something is not here. So somebody measuring here thinks it's the vacuum, right? Okay. Does the state have this property? Okay, but does it have this property then? You see, it doesn't have the property because let's say we compute this. What you'll get will be phi of x, O, phi of y, and then there's an integral. Right, this is what you find. Right? O will commute, you're right, but see what that will give you. O, phi of x, phi of y, 0, f of x, f of y. Phi of x, phi of y acting on the vacuum is not the vacuum itself, right? The vacuum is not an eigenstate of phi of x, phi of y. Nor is it an eigenstate of phi of x multiplied smeared with f of x. So this is in fact not true for this state. Okay, so this is not a localized excitation. What do you need to do to create a localized excitation? Okay, you need to do something you need to do something small. You need to fix this formula a little bit. You need to do this. This criteria I want. Yeah. Right? You need to write the state this way. This is a unitary operator that acts on the vacuum. Okay. This operator is the exponential of the field smeared with something. And here I'm assuming again that f of x is a real function. So U is a unitary operator. Why is it unitary? Because it's the exponential of I times a Hermitian operator. It's unitary. So U dagger U is equal to 1. Okay, do you see that? Okay, does this state satisfy the criteria we have? Yes, it does. because this is psi, right? This is equal to psi O psi. What is the expectation value of this operator O in the state psi? Well, it's the vacuum with U dagger O U psi. Do you see this? Is this clear? Okay. But now note, remember that phi of x, f of x commutes with O. So the unitary operator also commutes with O. You know this, right? Take the exponential of something which commutes with some other operator, the whole exponential commutes, right? This is equal to when O is space like. What is this? U dagger U is 1. And this is true for all O that space like to R. Every equation, every. Okay. So to create a unit, to create an excitation which is localized in a region, what you need to do is act with a unitary operator that is localized in that region. That creates an excitation that's localized in the region. Okay. Is this point clear? This is actually an important point that you should be clear about. No, just acting with phi of x, f of x might have been a good try, but it's not actually a localized excitation. Okay. However, acting with e to the power I phi of x, f of x, acting with a unitary gives you a local excitation. In fact, if you think about quantum mechanics, unitaries are what we can actually act with. You're not allowed to act with Hermitian operators. You make measurements, but when you act, you always act with a unitary operator on the system. Yes, many unitary operators. There are many, so there's no unique localized excitation, right? I can excite this region by doing this, right? By doing something else, or I can whistle, or I can hit, I can do many things, right? So all of those things correspond to some smearing function. So there's no unique excitation. So this is not the only unique operator. You can make many. You can make like e to the I, phi of x, phi of y, f of x, f g of y, except this integral is still confined to the region. Right? This is also a unitary operator, and this acting on the vacuum will also give you something. Okay? Maybe I should write it. I need to be a little careful if x and y are not space-like regions about how you commute them to make sure this operator is Hermitian. But I'm going to assume this g of xy is such that this operator is Hermitian if you're writing this down in your notes. Be careful that phi of x, phi of y, because phi at different times doesn't commute. You have to be careful that you smear it in a way that gives you a Hermitian operator. But let's assume that has been done in this function. Okay, so it's only unitary operators that create local excitations. These excitations then really do behave the way you expect local excitations to do, in that they spread at the speed of light, right? If you create an excitation here, if this is your region R, then this excitation will not have an effect on anything that is space-like to R, but it will in general have an effect to something that's time-like to R. So if you act with this unitary operator here, then it will have an effect in this region. This is your operator U that you acted with, right? You acted with U at this time, and no effect here. So this is exactly a localized excitation that's propagating forward, okay, at the speed of light. So this is what you mean by localized excitations in a quantum field theory. Now we can actually conclude our discussion of what we said the other day, which is you can already have this one does not movie. Let's hope. You can see that these kinds of excitations are never single particle excitations. Okay? Why are they never single particle excitations? Okay, so localized excitations are never single particle excitations. In fact, it's clear, right? Because how did we create our localized excitation? By the way, what I'm saying right now is not in the either the Coleman's lecture notes or in Peskin and Schroeder. It must be in some textbooks, but I don't know where. So this might be a good point to make sure you have notes. Okay, so localized excitations are never single particle excitations. Okay, and you can see why, because this looks like what? It looks like 1 plus I integral f of x I of x dx minus half so on, right? Acting on the vacuum on to infinity, right? Now, remember, what was our field? Our field had one creation operator and one annihilation operator. So you look at one field, this creates single particle states. But this will create double particle states. It might also give you some component proportional to the vacuum itself, but it will also have a term that creates 2 particle states. And this will create 3 particle states, and so on. Those higher particle states are suppressed by some 1 by n factorial times higher powers of f. So if you take f to be very small, maybe you can approximate it this way. But in fact, these terms always exist. So single particle states always have so localized states always have some component of arbitrarily high particle number. Okay, as you see here. Okay, so they're not single particle states. And that's precisely because they're localized. If you think about it physically, if you think that something is localized, then there's some uncertainty in its energy because it's localized, right? If there's some uncertainty in its energy, there's some component of that uncertainty that allows, that says that more particles can be created in that region. So if you localize an excitation, it's not a single particle state. This is how we started our discussion of quantum field theory. So now we have kind of developed the formalism of quantum field theory. We've set up creation annihilation operators. We've set up the Hilbert space. This is what localized excitations really look like, and they are not single particle states. They're never single particle states. Okay. No constraints. Here, I just assume they're real, and they're confined to the region R. I mean, so there's some local, they're confined to some region R, but there's no other constraint. I mean, some constraint meaning it has to be a regular function and shouldn't be singular and so on, but that's understood. Other than that, it's whatever you like. And that's because, there is a wide variety of excitations you can create in a region. It's not surprising. We physically think this chalk is an excitation about the vacuum here, right? Not somewhere else. So quantum field theory doesn't prevent you from localizing excitations. This is something you should remember. When we say there's no position operator, it doesn't mean there are no localized excitations, but there are no localized single particle excitations, as you see from here. Okay, good. Is this understood? This point that we want to see? Okay, very good. So okay, good. So now I want to go on to discuss symmetries. By the way, this is lecture 6, right? Excellent. Okay, good. So I want to now conclude. So this is the conclusion of our discussion on causality. And I want to move on and talk about symmetries. Are there any questions about causality? So, I want to do some recap because, this is kind of one important juncture where we reached. Right? And I just want to recap once more where we started. We started with the idea that, you needed fields. You needed fields for interactions. But we also needed fields because there was clearly no position operator in a relativistic quantum field theory. It didn't make sense. It violated causality. And so then we said, well, you should think of instead fields, which make sense from a relativistic viewpoint. Even in electromagnetism, you have fields. Then we started describing these excitations of fields. And now we have quantized the field. We have constructed the Hilbert space. We've constructed the Fock space, which is important. We've also discussed another representation of the Hilbert space, which is the Schrodinger representation. And we've discussed how causality is manifested. It's manifested in that equation. And we've also explained what localized excitations really are. They're unitary operators from a region acting on the vacuum. and these unitary operators are not single particle states. So we see where we were going wrong in the beginning. Some of you also asked, what if I took a single particle state K and just looked at the integral dk e to the ikx? Would that not be a localized state? No, it would not be. You would have to do something like this to create a localized state. Okay, so this is one chapter that we can conclude, and now I want to go on and discuss symmetries. Okay. Huh. It's just something, it's some linear combination of single particles. You can, but you claim, what will you claim? Sure, you can claim. It's not a localized state, that's clear, because it doesn't satisfy this property. Remember, what do we want from a localized state? We want the localized excitation, right? We want this. A localized excitation should have the property. By the way, you can think of additional excitations on top of psi. You can say that psi prime has a local excitation with respect to psi, if, or the other way around. By the way, you can, saying what has an excitation is always a little ambiguous. If let's say you have two states which have the property that if you give me some operators, O I'm using now for the same, O I'm indicating where O is in brackets, so that when you have operators in a region, I'm writing this because it doesn't have to be one field, it can be products of fields or something. Then the two states have unequal expectation values. But when you think of states, you think of operators which are space-like to this region R, then the expectation value of all such operators is the same. If you have two states of this kind, you can say, well, this state psi prime has an excitation with respect to this state psi. One good choice of reference state is to say vacuum, because then it makes sense to talk of excitations about the vacuum. I mean, in principle, we don't have to do that. We could say, here's this room, and this room is not the vacuum, of course, because it has the building. And then we get a chair in, we say that's an additional excitation. That's of this kind. There's already a state which already has the building and the room and so on. And then you put one more excitation on top. That's what this does. Okay. You could also remove things, of course, but okay. So now this is what we want from a localized excitation. The state you're talking about doesn't have this property. You can check. You can just do the calculation. But that's not hard to check. I mean, it's yeah, it's very easy to check that the state you're talking about just doesn't have this property. It's a state of the kind we were discussing first, like phi of x, f of x, just acting on the vacuum, and that doesn't have the property because you can easily. Okay, good. By the way, if you guys want to reduce the AC there, you should do that. I hope that's not too cold, right? Okay, I'm generally happy with colder temperatures, so I've reduced these ACs. If you like to keep that warm, you can do that. But I'll give you guys the remote if you want. It's up to you. Okay, good. Okay, so this is our discussion of causality. Oh, these ones, please keep cold. But those ones you can keep, or you can make whatever you like. Okay, good. So, okay, so now I want to discuss the question of symmetries. And I want to discuss a very important result, which is called Noether's theorem. There are other kinds of symmetries also that we can have, but I want to discuss today the simplest kinds of symmetries, which are, or I don't know, simplest or not, but one important class of symmetries, which is related to Noether's theorem. Okay? So what do we mean by saying that an action has a symmetry? What we mean is that we have an action, right, which corresponds to some field phi. We have a Lagrangian. L is some Lagrangian. Let's say there are multiple fields, just for generality. Okay, we could have many fields, not one field, but many fields. And we have some Lagrangian that describes how those fields interact with each other. So far, we've only discussed free fields, and for some time, we'll discuss interactions in some time. So we don't quite know yet how to deal with interactions. But you can imagine that you can write down some Lagrangian that describes some interacting fields phi I, or maybe free fields phi I. Yeah? Okay. Then, what do we mean by saying that this Lagrangian has a symmetry? What we mean is the following. We mean make a change phi I to some phi I plus lambda into delta phi. Let me call it d phi I. This d phi I is not necessarily small. I've put in a parameter lambda. This is a small parameter. This d phi I might be phi I itself. So this d doesn't mean small. Lambda here is keeping track of the small variation. Is this clear? Let's say you make a small variation. Okay? Let's say we change the fields in this way. And of course, when you change the fields, you have to change the derivatives also. That's understood. Then is the same. Yeah. Say this happens. Okay. Then we say that this is a symmetry. So say this happens, then we say L has a symmetry. Okay, under this transformation. Okay. So this is what it means to have a symmetry. What is the point of saying that the Lagrangian changes to L plus lambda? Say first that K was 0. Then what we are saying is that when you change the field in some way, the Lagrangian is invariant. So it's clear that that's a symmetry. Right? Because what we are saying is you have a field, you change the fields in some way, and yet the value of the Lagrangian doesn't change. Okay? And that's intuitively corresponds to what we mean by symmetry. For instance, let's say you have a field and you shift the field by a constant. Like you take phi to phi plus constant and say that the Lagrangian doesn't change. And clearly, that's a symmetry of the theory. It's some invariance of the theory. Okay. Now, say the Lagrangian changes in this way by a total derivative. Right? Remember, what really controls the theory is the action, right? And under that kind of a change, you see that S goes to S plus integral d4x d mu k mu times lambda. But this is 0 because this is a total derivative. Okay. Okay. So this is what we mean by saying that there's a symmetry, that there is some transformation you can make to the fields, which leaves the Lagrangian either invariant or changes it by 2. Now it's important that this should happen for all field configurations, not just for some special field con. Not just for those that satisfy the equation of motion. Why is this important? Because let's say we are only looking at those field configurations that satisfy the equations of motion. Okay. Then you see this is just identically satisfied. Because if we happen to be making small variations around field solutions of the equations of motion, then those solutions are defined to be those field configurations around which the action doesn't change under small variations. You see? So when we say there's a symmetry, it means we are not looking at one particular field configuration and saying, oh, when you're around this field configuration, if you make some change, nothing changes. In fact, the equations of motion are those field configurations around which the Lagrangian is unchanged under small variations. So when we say a Lagrangian has a symmetry, what we mean is that even if you look at an arbitrary field configuration, and if you change the fields in this particular way, let's say you look at some arbitrary field configuration. On that field configuration, the Lagrangian has some value. Even there, if you change the fields in some way, the Lagrangian doesn't change. That's what we mean, or it changes up to a total derivative. That's what we mean by saying that the Lagrangian has a symmetry. And when it has a symmetry, then we will now show that when the Lagrangian has a symmetry of this kind, there's a conserved quantity that you can find. That's called the Noether current, and also a conserved charge. Okay, is it clear what it means to have a symmetry? Okay. Now, Noether's theorem is a statement that when you have such a symmetry, you can get a conserved current. And I want to show you where that comes from. Okay. So say that this is true, right? So Noether's theorem is that when L has a symmetry, we can find a current such that d mu j mu equal to 0 on the equations of motion. So we are going to find some quantity, some current, which has the property that when you look at solutions of the equations of motion, d mu j mu is equal to 0. Okay. The original symmetry, remember we demanded, was off the equations of motion. It was off shell. The current is going to be conserved only when you look at solutions of the equations of motion. Okay. Okay. So let's see how we prove this theorem. It's actually pretty easy to prove. So remember, what do we said that L changes that way, right? But how much should L change under variation of phi goes to phi plus di phi? Well, we've actually done something similar, right? This is the change because of change in phi. And then there's one more term which comes from okay, and this is equal to right by assumption. This is the change in L. Okay. The lambda is now not going to be important anymore because this we just needed to do first order. This is actually the equation that we have. The lambda is just a parameter. So delta L was lambda into this, but since delta L was lambda d mu k mu, the equation we have is actually this. You see? Okay, good. Now we have this equation, and now notice that when you're in the solutions of the equations of motion, what you want a functional derivative, you mean this? d phi is just some change. It could be a constant also. What do you want? You want function? Maybe I should have written functional derivative. What do you want? It can be a function of phi. So what is wrong? Del L by del d phi. This. No, no, no. You see, phi is changing by phi plus lambda times d phi. Say phi is changing by phi squared. Phi is going to phi plus lambda phi squared. How much is the change in L? Well, the L is delta L by delta phi times phi squared times lambda, not delta L by delta phi squared. Right? Phi is changing by phi. Let's say phi is changing by phi plus phi squared, lambda phi squared. And the change in L is given by delta L by delta phi into phi squared, not delta. No, so let's say phi. Let's say phi. This is what we're calling d phi, right? How much is the change in L under this? The change in L is delta L by delta phi into lambda into phi squared, right? But this is only delta of delta phi. This is d phi. This is what we're calling d phi. You understand? Okay. When we are on shell, we have another relation. On shell just means whenever we are a solution of the equations of motion. Okay, that's what on shell. Right? This is what the equations of motion told us. But this means that this equation you can write as d mu times d phi plus sorry guys, I should have been putting sums of I here because I said at the beginning we have multiple fields. Okay, so I was assuming, if you like, you can assume a summation convention, but you know, when there's a phi I here and phi I here, and of course you have to sum over all i's. Yeah. Right. Okay, but now notice this left hand side is just a total derivative because it's d mu of delta L by delta mu of phi times d mu times d of phi I. This implies and that means that and this is what we call J mu. This is another current. Here, the Noether current is really, you know, just re-expressing the content of the equations of motion. It's not doing something that's, you know, that's different from the equations of motion. To derive the Noether's current, we use the equations of motion. Okay, so the Noether current is not re-expressing, you know, is not giving us something that's different. Second, note that the Noether current might sometimes be slightly ambiguous. It might be slightly ambiguous because there are always some quantities that just have identically zero divergence. Right? For instance, you know, let's say you considered some vector which looked like epsilon mu nu times d nu phi. Okay. Say I consider this vector. So you came up with some Noether current. Well, whatever theory, we'll come up with some Noether currents, right? I said, aha, but my Noether current is your Noether current plus this P mu. Okay. And there's no way we can actually fix things because d mu of this is 0, just definition. This epsilon mu nu, by the way, is what's called the antisymmetric tensor. Okay. So this epsilon, this is just 0 identically. So there's no way we can settle our dispute. And then, we just have to resort to good sense or convention. Okay. So, the Noether current is not necessarily something that's unambiguous. Okay. But usually there's a, these kinds of things, of course, you can get rid of or you can add these things which are identically 0. But usually there's a good symmetry reason to pick such terms or not pick such terms. Okay. This is a non-trivial statement. The fact that there's some ambiguity is kind of a side note. Okay? And this is a non-trivial statement, and it really re-expresses the content of the equations of motion when there's a symmetry. Everything you get from Noether's theorem, you could have got from the equations of motion, because after all, we use the equations of motion to get it. But this is often a very convenient way to derive conclusions without actually having to do the whole calculation. And that's why symmetries are so important. Because often calculations in field theory are hard and symmetries provide a guiding principle. Okay, excellent. Now, when you have such a current, you also have a conserved charge. Yeah, it's classical. That's right. It's classical. I'll give you a quantum mechanical thing also. But remember, even classically, when you look at operators, they do satisfy the equations of motion. Sorry, even quantum mechanically, operators do satisfy the equations of motion. You'd have to look at the Hamilton equation of motion for what? No. Remember, the equations of motion are still true also in the quantum theory. They're true as operator equations. These ones. Where we use them? I deleted them. Anyway, the equations of motion are true also in the quantum theory. These equations of motion, the Euler-Lagrange equations that we got, the operators also obey those equations of motion. What you might need to be careful about are questions of operator ordering, but barring questions of operator ordering, the operators also obey the equations of motion. So, Noether's current is still a good current, is still a good theorem even in the quantum theory. I'll give you another thing which is sometimes used at the level of the path integral. But remember, these equations of motion are not just classical equations of motion. These are also obeyed by operators in the quantum theory. You get some equations of motion, and the quantum operators also obey those equations. The issue here might have to do with operator ordering, but barring those subtleties, the quantum theory also obeys those equations. No. This is this is something that you show in non-relativistic quantum mechanics. Right? These equations are, after all, this is no. It's not a postulate. It's these equations. Let's see. These equations are precisely what tell you that I mean, these equations are the same as saying that the fact there's an equivalence between the Lagrangian equations of motion and the Hamilton equations of motion, right? And the Hamilton equations of motion you usually write as a Poisson bracket, and the quantum theory you promote that to a commutator. Yeah, sure. I mean, by the way, in the theory that we had right now, we had a classical equation of motion, and the quantum theory also obeyed that equation of motion. It's not like the quantum theory also obeyed box plus m squared phi is equal to 0, as did the classical theory. So this proving the equivalence of this to this is just the question of proving the equivalence of the Hamiltonian formalism to a Lagrangian formalism, which you've probably studied in classical mechanics. So once you prove the equivalence of this, this follows. So when you think of operators, operators also obey the equations of motion. As I said, there's a subtlety there which has to do with questions of operator ordering. And that subtlety, does sometimes arise for Noether current also. You have to be careful about, operator ordering and what happens when you multiply things at a point. And that in the quantum theory you always have to be careful about. But in fact, in this course, I don't think we'll ever encounter it. But you will encounter it, for instance, when you ask questions about how you define the stress tensor in the quantum. Okay, good. So, yeah. When you have a conserved current, you can also define a conserved charge. You see, this equation of motion is telling you that d0 j0 plus di ji is equal to 0. By the way, the reason we have a plus here is when you have one lowered and one raised index, that's just how you sum. Okay. If I try to raise the j0 or lower the j0, I would have to put a metric, but this way you just sum this. Okay. Now, if this is the case, let me integrate this over all of space. This is the equation I wrote here, which is d mu j mu is equal to 0. You see that? I'm seeing some blank faces. So, are you understanding this or not? Okay. I mean, this is just means the sum of 0, 0 plus 0 is 0. If I integrate 0, I get 0. However, notice that this is a total divergence. Okay. So, provided that your fields die off at infinity, and really, when you talk of operators, you always assume that because you're always talking about taking these operators and integrating them with functions that die off at infinity. So, this is always 0. So, this you can just cross out. So, it tells you that this integral itself is conserved with time. So, del 0 q is equal to 0, where q is equal to j0 d3x. That's why it's called conservation of charge. It's called conservation of charge because something is not changing with time. Notice Noether's current has two forms. There's one which is telling you d mu j mu is equal to 0. This is a local equation. It holds at every point in space. There's some j mu which you can define at every point in space, and it's conserved. And then there is some other thing which you can define at an instant of time, not at a point in space because it's an integral. And Noether's theorem tells you that that is conserved as time evolves. Okay. Okay. And this is, in fact, you're already familiar with this. In fact, all the charges that you have seen so far, all the charges that you have seen so far are of this form. Well, this includes the electromagnetic charge, right? Which you have heard of conservation of the electromagnetic charge. The electromagnetic charge is of this form. You've heard of conservation of energy, that's of this form. You've heard of conservation of momentum, that's of this form. We'll see that all of these electromagnetic charge, we'll see, and maybe you already know about this from classical mechanics for energy and momentum, that all, these conservation laws all eventually arise from symmetries in Noether's theorem. Okay. Okay, but the derivation is very simple, and as I said, it just follows directly from the equations of motion and seeing that there's a symmetry. I want to give you an alternate derivation of the equation of motion that's sometimes useful in the quantum theory. This is also fine, but I want to give you another derivation just so you're familiar with it. Okay, is this clear by the way, what I said so far? Okay, good. The other derivation is kind of at the level of the action as opposed to the level of the Lagrangian. It's really a very similar derivation, but sometimes this is used. And I remember first time seeing it, I was a little confused when I was a graduate student, and so I want you to be confused. Say you have a symmetry under this, okay? S is invariant. Okay, I'm giving you an alternate derivation. I'm going to reach the same result. Say S is invariant, which is what we want to say, right? We want to say the action is invariant. Here, lambda is just a number, and we do this. Now imagine a space-time dependent variation. Okay. Say I make this variation. What should happen? Is the action still going to be invariant under this kind of a variation? Yes, no, there are only two options. No, the answer is no, because we didn't assume it. We just said, let's say phi is invariant under phi goes to phi plus constant. Okay. Let's say phi is invariant under phi goes to phi plus phi 1 plus phi 2. Okay. Then I'm not allowed to say phi 1 plus e to the minus x squared times phi 2. Right? I'm not allowed to do that. That's a different variation. That's something where I'm modulating things in space-time with some function that I put in. So if you make this kind of a transformation in general, the action is not invariant. However, because it was invariant under phi goes to phi plus lambda, we know how it will change. Okay. So we know that the action, must change like at least the Lagrangian must change like L plus lambda of x d mu k mu, okay, plus some d mu lambda of x p mu, okay, so that the action changes like what I've done here is actually nothing very deep. All I've done here is I've said, the action has to change to first order and lambda, right? It has to change to first order and lambda because you're only keeping track of terms which change to first order and lambda. Well, what can the action really do? Whatever the action does, right? Whatever the action does, like it can have some term that looks like this, lambda of x times d mu k mu. Plus, it can have some term that depends on the derivative of lambda of x times this. It can't have some term that depends on lambda of x times just p mu nu, because if it had that, then that term would have contributed even when lambda was a constant. You want something which when lambda is a constant integrates to 0. This term has that property because when lambda is a constant, it clearly integrates to 0. And then this term is something which doesn't contribute when lambda is a constant. Okay. Okay, good. But now you see that this I can just write as S into lambda of x of d mu, maybe I missed my, anyway, k mu plus p mu. Oh, sorry, I should minus. This I got just by doing the integral of this term by parts, right? So this I got just by doing the integral of this term by parts, by writing this term as lambda of x and shifting the derivative to this side to write it as lambda of x times d mu p. But now remember that on solutions of the equations of motion, S doesn't vary under small variations at all. On solutions of the equations of motion, for this, we know S doesn't vary under any kind of small variations. It doesn't vary under these kinds of small variations or any kind of small variations, right? This is just a statement that when you're on solutions of the equations of motion, S doesn't vary. There, it also doesn't vary for these kinds of variations. But if it doesn't vary, it must be the case that this is 0. Okay. Now we can go back and ask, what is P mu? Well, P mu is just coming from here. It's whatever multiplies d mu of lambda of x. Okay. And that is just given, just by seeing how phi changes. Okay. And just by so that is just given by seeing how the Lagrangian changes under variations of this kind. And so you see this P mu is just given by the variation of the Lagrangian. Because that's the part that changes with respect to d mu of lambda of x when you make this kind of a transformation. Right? Which is the answer that we had for our current here. Okay, and k mu is whatever the boundary term was. Okay. Okay, this reaches us to the same conclusion that we had earlier, but let's now see some examples. We did a lot of abstract variations. Let's actually see how this is implemented in practice. So I want to do a couple of examples. I realize I'm going slower than I wanted to go, but let's do the first example, which is okay. So let's look at charges corresponding to these time. Okay, let's look at charges corresponding to space-time translations. Okay. So let's consider the variation x mu equals to x mu plus a mu. Okay. In the kinds of theories that we have been considering, where L doesn't depend explicitly on any position, where we have the integral of a field, integrated over all of space-time in the action, this is a symmetry. right? Okay. Now I want to write this in the language that we have. The language that we have didn't say what if you do x goes to x plus a mu. It said, you should change the fields in some way. However, changing x going to x plus a is the same as changing the fields as writing phi goes to phi plus a mu d mu phi. Whether you put a plus or a minus sign here, it depends on whether you interpret this as an active or a passive transformation. I interpreted it as an active transformation. Okay. So this is this, the statement is that for the fields, when you have a Lagrangian which doesn't depend explicitly on position, making x goes to x plus a mu is the same as taking phi of x to phi of x plus a mu. And for small a, that's like saying you take phi to phi plus a mu d mu phi. Okay. Let me put a lambda here just to keep track of. Okay. And then this is d phi. Okay. This is the same transformation. You see that it's the same. Now, what happens to L? What is K mu for this case? Okay, why don't you guys spend 2 minutes thinking what is K mu for this case? Is there a K mu? Is L invariant under this? Or does L change? And if it does, how does it change? Does it change by total derivative? We don't say the answer, but just think about it. Did you get it? Okay, good. You see, sorry, are you still working on it? I'll tell you what the answer is. Okay. You see, L itself is a scalar. So L itself also transforms this way. This is the Lagrangian density. So this is K mu. Okay. A mu here is just a translation. It can be any vector you like. You can take, A mu can be any vector you like, and corresponding to every such vector, there is a K. This A mu allows for translations in all 4 directions, in time as well, or in space, or wherever. Okay. So this is K mu here. Okay, then it's simple. Then you find what is the J mu. I just wrote it in this way to make things clearer in a second. You see, what is the current we have? Well, it's delta by delta of d mu phi, whatever that is going to be, times the variation of phi. But what is the variation of phi? The variation of phi is this. It's a mu d mu. This is a dummy index. So I can write it as a nu d nu phi. Is this clear? Then minus the current itself, which was a mu times L. I'm just choosing to introduce a delta mu nu and write this as delta mu nu times a nu times L. Is this clear? This is the same as what we have on the left hand side. This is d phi. This is K mu. This is what we call the Noether's current somewhere here. This is what we have. There's only one field here. If you like, there can be multiple fields. You can put a sum over phi, sum over I. Is this clear? This is the same as what we have. Okay, I'm seeing some blank faces. I'm not sure if I'm not explaining things or if you guys have already familiar with this, or there are no questions. Or you might have seen this already in classical mechanics, but although it's still good to go through this. Okay, if there are questions, as I said, feel free to ask. Okay, so this is the Noether's current that we have. Now remember that this current must be conserved for all possible A mu. Well, if that is conserved, then it must be in fact that the coefficient of A nu itself is conserved, right? Because it's conserved for all possible A nu. Right? So in fact, E mu nu is conserved. Okay. In that, d mu E mu nu is equal to 0. And this is called the stress tensor. And this is a very important quantity. Okay. And of course, we can raise the index. So I can write E mu nu when you raise a delta mu nu, you get an eta mu. You can write E mu nu in this way, or you can write T mu with one mu. Okay, this is called the stress tensor, and this is conserved. Okay, let's check a few cases. Let's check what happens for T00 or T0i. Let's take the case where, you know, what is T00? Well, you just put mu and nu equal to 0 in the expression that's hidden, and then you will find delta L by delta phi dot times phi dot, right? Minus eta 0, 0, but eta 0, 0 in the conventions we have is right, minus L. Do you recognize this guy? This guy is just pi. Okay? So this is pi phi dot minus L. And this is the Hamiltonian density. Actually, the Hamiltonian density, an integral to T00, 0. This is the conserved charge, is H. And Noether's theorem tells us that D0H is equal to 0. The Hamiltonian energy is conserved. Okay. Well, what about T0I? Well, T0I is just del L by del phi dot times di phi. And there's no other term here because eta 0i is 0. Okay. What is this? This is pi di phi. Do you remember at some point we discussed the momentum corresponding to translations? Okay. So pi Pi is equal to integral di phi. I want to say something about the conventions that we have. Notice in the conventions that we have, P capital I is minus P small I. Okay, and I think in the earlier lecture we were using P capital I. So that's because in our conventions, when you raise the spatial index, you get a minus sign. Okay, and this is the momentum, spatial momentum. And once again, Noether's theorem tells us that this is conserved. Okay? Notice that the conservation of H has to do with symmetry under translations, under time translations. Remember, where did this come from? It came from the fact that our Lagrangian had no explicit time dependence. That is why you were allowed to make x0, x goes to x plus a mu. Let's say we didn't have spatial, for some reason we had some theory in which we couldn't make spatial translation, but we could still make time translation. This Hamiltonian will still be conserved because you could make x goes to x plus a. In this theory, somehow the background has spontaneously broken Lorentz invariance. Okay? But yet in the frame that we still have x0 goes to x0 plus a0. And this is still some conserved charge that you get. Okay. Actually, what I said is unnecessarily complicated. In the theories that we'll consider in this course, okay, we'll always have translations. We'll have symmetry under all kinds of translations. And in particular, because you have time translations, and because you have that symmetry, you see that the energy is conserved. And because you have symmetry under spatial translations, momentum is conserved. So you see that the conservation of energy and the conservation of momentum have to do with the symmetry of the action under translations in space and time. At some point when we discussed the momentum, we derived it in a slightly ad hoc way, maybe by just saying that momentum generates spatial translations and this has the right commutation relations. You can think of this as a more systematic derivation of the same result. Okay. Good. Let's consider one thing, and then actually maybe I can stop. I said I'll stop a little early. What about the theories that we have been considering, right? In most theories that we consider, not in all, but in most theories that we consider, and in fact in the theories we'll consider in this course, for most of the course, remember L has this form. Remember, this is in the free theory, for instance, and there's all V of phi is just m squared phi squared. I forget what conventions we used. I think we wrote m squared phi squared separately. In the free theory, V of phi is 0, and you have this term. And in some other interacting theories, like the ones we'll consider a little later in the course, V of phi will be non-zero. These are the common Lagrangians that we consider. In this situation, notice that this simplifies a lot because delta L by delta d mu phi is just d mu phi. Okay. And then the stress tensor is just d mu phi minus eta mu nu L. And it's symmetric in that T mu nu is the same as T nu. This formula, by the way, is not manifestly symmetric. Okay. It might sometimes give you a stress tensor which is not symmetric. But then you can often use this ambiguity that we discussed earlier to find a stress tensor that is symmetric. Okay. However, in any case, in these theories, the simple kind of theory that we'll consider, the stress tensor is explicitly given by this, it's symmetric. And this contains all these conservation laws that we talked about, the conservation of energy and the conservation of momentum. And let me remind you, this is the current this satisfies d mu T mu is equal to 0 as a local equation, and corresponding to that, we have 4 conserved charges. Why 4? There are 6 components of the stress tensor because you have d mu T mu is equal to 0, but there are 4 conserved charges that you get, because you have T00, you have T01, T02, T03. So you can change the various values of mu and you'll get one conserved charge by integrating the 0 component by setting mu equal to 0, or alternately by setting mu equal to 0 and changing the new values. Okay? So you'll get one conserved charge for each value of mu, and therefore you'll get 4 conserved charges, which corresponds to 1 energy and 3 momenta. You see? So the stress tensor gives rise to conserved charges like we discussed in the slide that has been erased, or in the blackboard that's been erased. And the stress tensor itself satisfies a local equation. And if you integrate the stress tensor space, you get a conserved quantity. Depending on which component you integrate, provided you set one of the indices to 0, you'll get a conserved charge, and there are 4 kinds of conserved charges. Okay, good. So that's all I want to say. In fact, I'll stop here since I said I'll stop a little early. Are there any questions about this? Yeah, sure. So these are, pressures and stresses and strains and so on. So this is the stress energy tensor, right? So if you put both spatial indices, those do have significance. This is something you've studied also in stress and strain and so on, right? When you study stress and how things respond to stress and strain. So those things, it's not like those things are not significant, but the conserved charges come by looking at the T0i. Those things are important because when you look at this equation of motion, this requires those things, right? There's local conservation of energy. It's not just that an energy is globally conserved. Energy is globally conserved, but it's also locally conserved. It's not that energy can, you see, global conservation might tell you, well, maybe something can vanish from here and appear somewhere else, but that doesn't happen. Things are locally conserved, and those components are important for that. It's not like those components don't appear here, they will appear here. You see? Okay, good. Are there any other questions?
Yes, sir.
Yeah.
Here we have considered like differentiation, integration, and also it is all for continuous. Like, for what about like barrier number conservation law? Is there any symmetry associated with that?
Some of those things we'll discuss later. Barrier number conservation and so on have to do with what are called accidental symmetries. We'll discuss that later. They have to do with maybe once we've discussed the interactions and so on, what accidental symmetries are.
Okay, sir. Thank you.
Haven't even discussed anything corresponding to charges yet. So maybe if you ask me that question later, I can try and explain.
Okay, sir. Okay.
Yes. So we'll discuss that next time. So so this is under translations, the charges that we've got. You can also consider currents under Lorentz transformations, and the angular momenta is one class of such currents. We'll get it next time. It basically corresponds to slightly more complicated transformations, where x mu goes to x mu plus epsilon nu times x mu. We'll discuss it, and you'll get some similar expression. You'll just get factors of x and so on. Yeah, well, the Hamiltonian density. Yeah, that's right. That's right. Yeah, we'll do it. Yeah, that's correct. And that's just saying the center of mass doesn't change, right? Xi times the if there's nothing, the center of mass doesn't change. Correct. Center of mass sits where it is. I'll do that explicitly next.